Hello everyone, welcome back to IITian Club. In this video, we'll be quickly revising the first chapter of physical chemistry, solutions and its colligative properties. Without wasting any time, we'll start the video. First of all, we all know that solution is solute plus solvent. For example, if oxygen is dissolved in a water, solute is oxygen and solvent is water. The next topic is concentration terms. This is the most important topic, the most foundational topic, I would say. This will be used in entire physical chemistry. Three most important concentration terms which are asked more frequently in JEE mains is molarity, molality and mole fraction. Molarity is number of moles of solute per liter of solution. That is moles of solute divided by volume of solution in liter. That you have to note. The next one is the molality. Molality is denoted by small letter m. Molarity is denoted by the capital letter M. Molality is moles of solute divided by the weight of the solvent in kg. In molarity, it was solution, and in this, it is weight of solvent. That you have to know. The next one is mole fraction. Suppose there are A, B, C in the solvent. The mole fraction of A would be number of moles of A divided by number of moles of A plus number of moles of B plus number of moles of C. And the most important thing in this concentration term is this temperature dependent and temperature independent concentration terms. Even in JEE Main 2024, this question was asked, the quantity which changes with temperature. In this thing, if you know this table, that is the which and all depends on temperature and which and all does not depend on temperature, then you will be easily be able to answer that question. So when it comes to temperature dependent, the concentration terms which depend on the volume become the temperature dependent, because with the temperature change, volume changes. So concentration terms changes. That's the logic behind it. Molarity, normality, strength, percentage, weight by volume, percentage volume by volume. All those things depend on volume, so they depend on temperature. Molality, mole fraction and percentage weight by weight. These concentration term does not depend on volume and hence they are temperature independent. The next topic is Henry's law. This law states about the solubility of a gas inside a liquid solution. It states that solubility of a gas in liquid is directly proportional to the partial pressure of the gas present above the surface of the solution, which you can see in the figure. In the figure, you can see some of the gases on above the liquid solution. The partial pressure of the gas above the solution is directly proportional to the solubility. So if the partial pressure increases, the solubility of that gas also increases in the solution. Mathematically, it is expressed as P is equal to KH into chi. KH is the Henry's constant and chi is the mole fraction of that element in the solution. Actually, we denote it by mole fraction because mole fraction is the denoting factor of the solubility over here. So the partial pressure is equal to KH, the Henry's constant, and X. X is the mole fraction of the gas in the solution. Hope you got this. And the next law is the Raoult's law. Raoult's law states that when you have a solution containing two solutes, that is A and B, the partial pressure of A and the partial pressure of B is directly proportional to the mole fraction of A and mole fraction of B inside the liquid. We'll be mathematically writing it like the total partial pressure above the solution A plus B is equal to P naught A XA, that is the mole fraction of A, and P naught B XB. P naught A and P naught B are the partial pressure of the pure solvent A and B without mixing. And graphically, we'll be denoting the Raoult's law like this. The next important thing which you have to note is, if YA and YB are the mole fraction of A and B in the vapor above the solution. Previously, the XA and XB were the mole fraction inside the solution. In this case, mole fraction of A and B in the vapor above the solution. Then the 1 by total partial pressure is equal to YA, that is mole fraction of A in the vapor above the solution, divided by the P naught A. P naught A is the partial pressure of the pure solvent A, plus YB plus P naught B. Based on this formula, there was a direct question in 2023. So please note this formula as well. Now we'll be moving on to ideal versus non-ideal solution. Ideal solution is a solution which follows Raoult's law. That is, the partial pressure above the solution is directly proportional to the mole fraction of that component in the solution. Non-ideal solutions are the solutions which does not follow the Raoult's law. Even in non-ideal solution, there are two cases. One is the positive deviation and another is the negative deviation. We'll be looking more into that now. In the ideal case, let's say you have two solutions, that is A and B, and the interactions between A and B are denoted like this, AA and BB. And when they come together as a solution, that when A and B form a solution, the interactions between A and B when they were individually present, and the interactions between A and B after will also be the same in case of ideal solutions. So when we mix both, the delta volume mix, that is the volume of A plus volume of B, will be equal to volume of A plus B. There will be no change in the total volume of the solution. Also, we have to note delta S mixing. Whenever we mix together, the entropy increases. That's what we know from thermodynamics. And delta H of mixing is 0 because there is no change in the interactions. If there is a change in between the interactions between AB, then there will be some change in the delta H, that is change in enthalpy. And delta G mixing will always less than 0. Only if the change in Gibbs free energy is negative, the process can spontaneously occur. So delta G is less than 0 for this ideal solution case. And when it comes to the non-ideal case, there are two cases as I mentioned. The first one is the positive deviation. In positive deviation, what happens is the interactions between A and B, that is A and B, after we form a solution of A and B, the interactions between A and B is less than the interactions between AA and BB. When this happens, the A and B molecules are free to rise up from the liquid, so they will easily convert to vapor. When they easily get converted to vapor, the vapor pressure also increases. That's what this diagram says. When you see the positive deviation, this is the regular graph which follows the Raoult's law. When this positive deviation occurs, that is the interactions between A and B are weaker than the interactions between AA and BB, so the vapor pressure increases. That is shown by this rise in the curve. And when we see the delta volume mixing will be greater because now the molecules are loosely packed. The A-B interactions are less. So the volume, there will be an increase. And always whenever we mix together, the entropy is positive. That you have to note. In every cases, the delta XS mixing, that is change in entropy, will be positive. And in this case, we have to set the energy. That's why the enthalpy is greater than 0. Always less than 0, only then the process can occur spontaneously. The next one is the negative deviation from the Raoult's law. In this case, the interactions between A and B molecules in the solution is greater. So, in the sense, it is more tightly packed, and the molecules cannot leave the liquid state and enter the vapor state. So, there is a depression in this graph. That is, the total vapor pressure will be lesser than the regular Raoult's law graph. That's why it is called the negative deviation. In this negative deviation, as the interactions between A and B are high, the delta volume mixing will be less than 0. And delta S mixing, as always, it is greater than 0. And delta G mixing is less than 0. Also, you have to note delta H mixing, that is enthalpy, is less than 0. There's a trick to remember all this. In positive things, everything is positive except the delta G mixing. In negative deviation, everything is negative except the entropy change. I hope this was useful for you. The most important thing which you have to note in this Raoult's law is the examples for positive deviation, negative deviation, and the ideal solution. These are the examples given in the NCERT, and these ones are the which I have organized so that you can remember it easily. When it comes to ideal solution, you can remember it as which has similar structures like benzene and toluene, N-hexane and N-heptane, bromoethane and chloroethane. All these are the examples of the ideal solution. When it comes to positive deviation, alcohol acetone mixture, like alcohol plus acetone solution, alcohol plus hexane solution, all these are positive deviation. All these solutions show positive deviation. And acetone plus hexane, acetone plus cyclohexane, acetone plus anything except acetone plus chloroform are aniline. Acetone plus aniline solution shows negative deviation. Why I would suggest you to remember all these examples is, in 2024, there was a question based on this. Identify the mixture that shows positive deviation from the Raoult's law. Make sure that you answer this question in the comments below. Don't forget to do that. The next question is also a solution of two miscible liquids showing negative deviation from the Raoult's law will have what? If it is showing negative deviation, what will happen? What happens to the vapor pressure and what happens to the boiling point? What happens to the boiling point you will be able to answer once we do the elevation and boiling point colligative property. So make sure you answer all these questions in the comments. The most important topic of this chapter is colligative properties. But before we move towards it, make sure that you subscribe to our channel so that you don't miss out any of our upcoming videos on electrochemistry, chemical kinetics, and inorganic chemistry. I hope that you subscribe to our channel, and now let's move forward. There are 4 colligative properties which are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Colligative properties are properties which does not depend on the nature of the solute or solvent. It depends only upon the amount of the solution, amount of the solute or solvent. Now we'll be dealing with each and every colligative property. The first is relative lowering of vapor pressure. For this, we'll be considering two cases. One is a solution with non-volatile solute and other is a pure solvent. In the solution which contains a non-volatile solute, the vapor pressure above it will be lesser than the vapor pressure of the pure solvent. This is because the non-volatile solute, non-volatile in the sense it does not get converted to vapor. If the vapor amount is lesser, the vapor pressure is also lesser. That's the logic. And we'll be quantifying this reduction in vapor pressure as relative lowering of vapor pressure. The lowering of vapor pressure will be P0A minus PS. P0A is the vapor pressure of the pure solvent, which is higher, and PS is the vapor pressure of the solution which contains the non-volatile solute. Because it contains non-volatile solute, the vapor pressure is lesser than the pure solvent. So this is the lowering. And relative lowering in the sense delta P by P0A. When you do the calculation, we'll be getting that relative lowering is equal to the mole fraction of the solute. B is solute over here. The next colligative property is elevation in boiling point. When it comes to boiling point, the vapor pressure should be equal to the atmospheric pressure. You should note that the vapor pressure of the solution is always lesser than the pressure of the atmosphere. So we will have to supply more temperature to make the vapor pressure to generate more and more vapor such that it creates a vapor pressure which is equal to the atmosphere. This is how boiling occurs. And when you have a non-volatile solute, like in this case, when you have a non-volatile solute, the vapor pressure will be reduced. You will have to supply more and more temperature to make the vapor pressure equal to the atmospheric pressure. So that boiling point will be increased, and this elevation in boiling point is a colligative property. Mathematically, we have found out that this change in temperature is directly proportional to the molality of the solute, that is molality of the non-volatile solute. And to remove that proportionality, we'll introduce a constant which is Kb in this case. Kb is boiling point elevation constant, which is also known as helioscopic constant and molar elevation constant. You have to know the formula, and based on the formula, we'll have more and more questions in JEE or NEET or any competitive examinations. I hope you got this concept. The next colligative property is depression in freezing point. In this also, we'll be having a non-volatile solute which does not get vaporized, and the vapor pressure will be reduced. In this case, the freezing occurs when the vapor pressure of the solution is equal to the vapor pressure of the solid. Vapor pressure of the solid is lesser than the vapor pressure of the solution. So the temperature has to be lowered to make it equal, and that lowering is termed as depression in freezing point. And delta TF is equal to Kf into M. Kf is the freezing point depression constant. And experimentally, we found out that delta T is directly proportional to molality. This was same with the case of elevation in boiling point as well. But here the constant to remove the proportionality is only different. Here it is Kf and there it was Kb. And then is the osmotic pressure. Osmotic pressure is equal to CRT. C is molarity, R is the universal gas constant, and T is the temperature. This is also temperature dependent, and osmotic pressure is denoted by pi. These are the three questions based on colligative property which came in 2024. You can try out these and let me know in the comments below. We'll be answering all these questions in the upcoming videos, so stay tuned. The next topic is abnormal colligative property. Abnormal colligative property occur when there is association or dissociation. Let's say you have a compound, electrolytic compound like NaCl. So when you put this into a solution, it gets dissociated into Na plus and Cl minus. So the number of ions is increased. When the number of ions is increased, the colligative property also increases. But actually, this is an abnormality caused because of the dissociation and association. To eliminate this, we'll be multiplying it with I. I is the Van Hoff factor. Van Hoff factor is defined as number of moles after dissociation or association divided by number of moles before the association or dissociation, I is equal to 1 for a non-electrolytic solution. So basically you don't have any errors in the measurements. But when it is an electrolyte like NaCl, there will be some dissociation or association, like in the case of CH3COOH. So we'll be multiplying a error factor, that is I, that is termed as Van Hoff factor. In case of association, as the number of moles after association is lesser than the number of moles before the association, the I is less than 1. In case of dissociation, it is the other way. I is greater than 1. We'll be multiplying this with each and every colligative property to get the corrected colligative properties. In case of RLVP, it is equal to I into the mole fraction of solute. In case of elevation and boiling point, I into Kb into M. Depression and freezing point, I multiplied by the original thing, Kf into M. M is molality of the solute. And in case of osmotic pressure, it is equal to ICRT. C is molarity, that you have to know. And in this, we'll be looking into dissociation and association into some depth. Let's say AN is getting dissociated into N different A's. That is this case. AN is a single compound and it is getting dissociated into N different parts. So if the initial, this comes from the chemical equilibrium part. If you know the chemical equilibrium, how to write these things, then this will be easy for you. Let's say there are initially C moles of AN and there will be no moles of A, and alpha is the degree of dissociation. Then from C alpha will be dissociated. So the moles of AN after dissociation will be C minus C alpha. And in this case, we'll be writing the stoichiometric coefficient also here, NC alpha. This concept we'll be covering in the chemical equilibrium part. If you have covered it already, you will be getting this very easily. From this, we'll be calculating I Van Hoff factor. That is moles after dissociation and moles before dissociation. We'll be adding all these C minus C alpha plus NC alpha. And when we do that, we'll be getting this result. And from this, we'll be getting the degree of dissociation. I minus 1 divided by N minus 1. The next one is association. In association, there will be N different B's. It can be anything like CH3COOH or anything. N different B's are getting associated into a single thing, and single thing will be denoting with Bn. And initially, the concentration of B's is C. And because of association, there will be some reduction, and that is degree of association will be B, and C minus CB, C beta, and this here it will be C beta divided by N. This comes from the stoichiometry. Here actually, as N is in the reactant side, here we'll be multiplying in the denominator side. Actually, we'll be dealing this more detail in the chemical equilibrium part. And from this, we'll be getting the value of I. I is the moles after association divided by moles before association. And when we calculate that, when we add all these things and divide it with C, we'll be getting this formula. I is equal to 1 plus beta 1 by N minus 1. And from this, we'll be able to get the degree of association. In some questions, we'll be asked to find alpha and beta. That will be covering in the question sessions following this. You can also try this previous year question, the current year question actually, and let us know in the comments. I hope this video was very helpful for you to quickly revise this chapter in single shot. And for more such awesome contents, stay subscribed and share this video to your friends so that they also don't miss out any of this best contents. And thank you for watching.